at points where there's top of the hill, or have we defined relative extrema? No, we haven't. We defined maximum and minimum in an absolute sense, but we did not define relative extrema. We talked about the extreme value theorem. I said if a function is continuous on a finite closed interval, then it has both of them. But we did not go on to talk about a relative maximum or a relative minimum. Now there is a kind of a fine difference between them. A lot of times they will happen at the same place, but we want to get kind of the distinction between them. So let's start there actually. That's going to work better for us. Relative maximum. Okay, we saw what a maximum is. If it's the maximum value of the function on the interval, then the maximum happens there. What does it mean for a function to have a relative maximum at x sub 0? Well, it has to happen like this. It will have a relative maximum at x sub 0 if there's an open interval containing x sub 0 on which f of x sub 0 is the maximum value on that open interval. So I think of it. I think of these as at the bottom of the valley or the top of the hill in ways that I don't necessarily think of an absolute maximum or an absolute minimum as needing to be at the top of the hill or the bottom of the valley. So I think of something kind of like that happening, where it's certainly not the lowest point on the graph, because we can go over here and over here and over here and over here and find lower points. But if there exists an open interval, that means open basically means we have to look on both sides of it. An open interval containing x sub 0 such that if we just restrict the function to that particular open interval, then on that interval right there, yeah, it's f of x sub 0 is less than or equal to any other function value on that interval, so it's a relative minimum. Relative minimum is the picture that I have here. So, so f has a relative minimum at x sub 0, like this. And turn that picture upside down, and then we get the relative maximum that I had intended to do first. Point at the top of a hill, so maybe something like that. This is our x sub 0, and clearly not the highest point on the graph. There are higher points on the graph. But if there exists an open interval containing x sub 0 such that if we restrict the function just to that open interval, that is the absolute maximum value of the function on that open interval, then f has a relative maximum at x sub 0. In either case, we call it a relative extremum, or say f has a relative extremum on the interval. So we keep this definition in mind, and then we look at the next theorem. Here is the theorem. If a function has any relative extrema, then they can occur in one of two places. Any relative extrema. They can occur in one of two places, where f prime of x equals 0. That means the tangent line to the graph would have a slope of 0. And what kind of line has a slope of 0? Horizontal line, straight across. Horizontal line. That has a slope of 0. And so when the tangent line is horizontal, that would be one possible situation where f prime of x could equal 0. And if f prime of x is not 0 and there's a relative extremum, it means that it's not differentiable. So if the derivative exists and f prime is positive, or f prime of x, I guess I should say, is negative, then it doesn't have a relative extremum at that particular point. So if we're looking for relative extrema, given an interval, we might say find all the relative extrema of this function on this interval. There are two things to look for. Look for points in the interval where f prime of x equals 0. That involves finding f prime of x, setting it equal to 0, solving for x, or looking for places where it might fail to be differentiable. That could be a place where we get a cusp or a corner in the graph, like the absolute value function. Or it could be that, well, let's see, we usually don't think of these as places where it's discontinuous, but a discontinuity certainly would be a situation where it fails to be differentiable. So those are the types of places we look for situations where a relative extremum may occur. Let's look at example 1 and see if we can see examples of where a relative extremum may occur or may fail to occur. A number, and this is important if not critical, I should mention this, a number where either f prime of x equals 0 or where f is not differentiable, that is a possible location of a relative extremum, is called a critical number. Now that's not to say that there will be a relative extremum at every critical number. We're about to see an example where f prime of x is equal to 0, where it's not a relative extremum. But we're saying that if it happens, if there's a relative extremum, it has to happen at a critical number. So it's important for us to come up with the list of critical numbers. Let me try this again. Capture that. Paste it. Find the critical number of each function and indicate whether or not a relative extremum occurs there. Maybe it will, maybe it will not. By inspection, I think we could do this if we wanted to use the chain rule and find the derivative. We could take the 2 out in front, reduce the exponent by 1, and then multiply by the derivative of what's inside the parentheses. The derivative of x minus 2 is what? 1, and don't forget to multiply by 1. And then the derivative of 1 is 0. Don't forget to add the 0. All right. So this is just going to be f prime of x equals, I could even leave it in factored form and that would be fine, 2 times the quantity x minus 2. The number that makes this equal to 0 is what? What's the 0 of this expression? Substitute 2 for x. It makes it 0. So 2 is a critical number. F prime of x is defined as a polynomial, so it's defined for all real numbers. So we don't get any critical numbers that way, where f prime is undefined, but we do where f prime is 0. So 2 is a critical number. Does it look like a relative extremum occurs there? Is it a point at the top of a hill or the bottom of a valley? Yes. Bottom of the valley, it looks like f has a relative minimum at x equals 2. I'm just getting that visually. There's a test for relative minimum, relative maximum that we'll look at in a little bit called the first derivative test. Not applying that, I'm just kind of looking at the picture and making that statement. On the other hand here, f prime of x equals 3 times x minus 2 quantity squared. We multiply by 1 because we have to follow the chain rule. Derivative of x minus 2 is 1, and then we add 0. So f prime of x equals 3 times x minus 2 quantity squared. What number makes this function equal to 0, this derivative? Still 2. So, just like 2 was a critical number here, 2 is a critical number here as well. Because it's a place where, I wanted to reach up and circle something, but I didn't paste it. It's a place where this happens. F prime of x equals 0. That makes it a critical number. Not the fact that a relative extremum might happen there, or not the fact that a relative extremum does happen there, but the fact that f prime of x equals 0. It gives the function an opportunity to have a relative extremum. But it does not take advantage of that opportunity, because we look at it, the point 2, 1 right there is not at the top of a hill, and it's not at the bottom of a valley. If we draw any open interval, that means we've got to catch points on both sides. Any open interval containing x equals 2, it will include both numbers with function values less than 1 to the left and numbers with function values greater than 1 to the right. So f of 2 equals 1, but 1 is not the maximum value of the function on that open interval, and 1 is not the minimum value of the function on that open interval. So f does not have a relative extremum at 2. So if it's going to have a relative extremum, it will happen at a critical number. But if we have a critical number, it may not give us a relative extremum. Let's look at these other two functions. Same directions. Find the critical numbers and indicate where if it's a relative extremum, and if so what, f of x equals the absolute value of x minus 2 plus 1. Now, we could get this information by inspection, or we could try to take the derivative. That's not the corner that I want it to be. I must not have had the scientific notebook choose enough points when it drew this picture. But there's a corner there. This is a translation of the absolute value function. We've dealt with that function before. We've shown that it fails to be differentiable at 0. So this one, hopefully it follows. When we translate it, just scoot the graph. This fails to be differentiable at 2. We could pull out the limit of f of x plus delta x minus f of x all over delta x approaches 0, and show this. We don't have the time or the will to do such a thing. So I'm going to say f is not differentiable at x equals 2. So 2 is a critical number. Does the function have a relative extremum at 2? If, I guess it would be an uncomfortable valley in which to dwell. But it's a valley nonetheless. So I think of this point as the bottom of a valley. So there exists an open interval, in fact any open interval you draw, containing 2, where f of 2, which is 1, is the minimum value of the function on that interval. In fact, f of 2 equals 1 is the minimum value of the entire function. Negative infinity to positive infinity if we want to go with that interval. So f is not differentiable at x equals 2. That makes it a critical number. F has a relative minimum at x equals 2. So two ways we get a critical number. We get a critical number if f prime of x equals 0, nice smooth bottom of a hill or top of a bottom of a valley or top of a hill, or maybe not the top of a hill or bottom of a valley either. But that's one place it can happen. Or we get a critical number when f fails to be differentiable at a number. But in either case, we may or may not get a relative extremum. So here's a case where we do, in the next case we don't. Because of this sharp turn, where the slope changes instantaneously from being m sub tan equals negative 1 to m sub tan equals negative 4, when there's an abrupt, discontinuous change in the slope, it's a point of non-differentiability. Corner in the graph, the derivative does not exist there. So f is not differentiable. I was about to say x equals 2 is a point of non-differentiability, but we'll go with this. Differentiable at x equals 2. F, does it have a relative extremum at 2? It's not the bottom of a hill, bottom of a valley rather, even a pointy valley, or the top of a hill, even a pointy hill, because any open interval that we draw containing numbers a little to the left of 2 and numbers a little to the right of 2 is going to have values greater than 1 and also values less than 1. So that 1 will be neither the minimum value nor the maximum value of the function on that open interval. So f does not have a relative extremum at x equals 2. All right.
So won't we just be able to look at those and tell that?
Pretty much. I think we can inspect the graph in virtually all cases and tell whether it has a relative minimum, relative maximum. But what we'd like to do, kind of in a global sense, is be able to get the collection of all critical numbers where such a thing might happen. Because in cases where it might not be obvious, we want to be able to say definitively these are the only places where it can happen. But if there's a particular x value in mind, we could probably figure it out by inspecting the graph. How do we find absolute extrema on finite, and by finite we mean bounded, closed intervals? So there's a lot to put together, some of which we talked about at the end of class last time. At the end of class last time we said if we have a function that's continuous on a closed bounded interval, it has both a maximum and a minimum, as one of each. If we lose the continuity, might not have one. If we lose the closedness of the interval, might not have one. But closed, bounded interval, continuous function, it will have a maximum and a minimum. So how do we find them? Well, we got a theorem. If f is continuous on an open interval AB, and if f has an absolute extremum on this interval, then it must occur at a critical point of f. If it has an absolute extremum, then it must occur at a critical point. Now let's look back at the definition of critical point and make sure we're clear on that. If a function has any relative extrema, then they must occur at critical point. Different calculus textbooks call these critical points, critical numbers, two different things basically. Some call them critical points, a point on the x-axis in the domain of the function. Others call them critical numbers because we think of numbers in the domain as numbers. So I'll use those interchangeably. So just from a terminology point of view, if I say critical numbers, if I say critical points, I'm not necessarily thinking of a point on the graph. I'm thinking of a point on the x-axis, I don't want to say one-dimensional, but just a number from the domain, not a combination of x and y coordinate, point on the graph. So we said relative extrema must occur at critical numbers or critical points. Here we're saying if we're looking at an open interval, then an absolute extremum that occurs on this interval must occur at a critical point or critical number of the function. So there's just two places to look. On the interior of the interval, we look for places where f prime is equal to 0. We look for places where f prime doesn't exist, where the function's not differentiable, if we're looking at the interior. And if we have the endpoints of maybe a closed interval, then we can look at the endpoints as well. So let's see what the guidelines are. Find the critical points in the open interval, list those numbers, evaluate the function at each of the endpoints, and then we have a collection of values. The absolute maximum value of the function is going to be the greatest of those numbers, and the absolute minimum value of the function will be the least of those numbers. So there's a lot going on there. Let me just draw a picture, and then we'll try this for an actual function. Suppose we've got a function defined on the closed interval a, b, and it has to have a value at a. Let's say it has that value. And then let's say it goes up like this and then turns. And so right there we're going to say this is x sub 1. And then it has a point where it just comes to a corner there, and it goes up like, what does it do? It goes up like this, and then it turns again, and it ends up here. So we've got x sub 2, we've got x sub 3, and b I'm going to call x sub 4, and a I'm going to call x sub 0. So if we're checking to see what's the absolute maximum value of a function, absolute minimum value of a function on a closed interval, it has one of each. What we would do is find where f prime of x equals 0. It happens there and there. Horizontal tangent lines. Nice smooth curve. And by smooth curve, I'm trying to draw the picture in such a way that the derivative exists. And then there's a place where f prime of x does not exist, right there. Try to go with a corner there. So a corner, it fails to exist, but still that's a critical number, critical point. And then that's an endpoint, and that's an endpoint. So what we do is we evaluate the function at all 5 of these numbers. So we say f of x sub 0, and maybe f of x sub 4, get the endpoints out of the way, and then f of x sub 1, f of x sub 2, f of x sub 3, and we have 5 numbers. 5 numbers. The greatest of those 5 numbers is the absolute maximum value of the function on this interval. Looking at the picture, what's going to be the greatest of those 5 numbers? So f of x sub 3, whatever we get there, get a number. This is the maximum. And what's going to be the least of those 5 numbers? I want to say maybe x sub 0. So in this case, it's going to be the minimum. Unfortunately for my picture, it ended up being the extremes. I didn't intend that, but I don't think there's anything to imply that it should always be that way. So sometimes an absolute extremum will occur in the interior of the interval, as the maximum does, where f prime of x equals 0, and sometimes it happens at the end point. But this is what we'll do.
This is always how we identify the critical numbers, just like that?
Well, for the critical numbers are 3.
Okay.
For this picture, it's x sub 1, x sub 2, and x sub 3. Okay. Critical numbers happen within the interior of the interval, and that's where either f prime of x equals 0, here and here. We get those by taking the derivative, setting it equal to 0, and solving for x. Okay. Our solutions to that equation are the critical numbers where f prime of x equals 0. And then we just kind of have to look at it and think, where might the derivative be undefined? For polynomials, it won't happen. We'll do several examples of polynomials, and we won't get any that way. But if it involves a radical, if it involves something where the functions piece together, if it involves absolute value, then there might be a point of non-differentiability like x sub 2, and that's an additional critical point, critical number. And then we also check the endpoints. Evaluate it. At all of those, pick the highest and lowest. So let's see, several intervals there, but let's consider the function. Find the absolute maximum and absolute minimum of this function on these intervals, and to save time, I've even gone ahead and calculated the derivative and put it in factored form. Wow. If only I would do that on the test, huh? Not too tough, really. We would find the derivative. It's just the power rule. 1, 2, 3, 4, 5 times. Power rule. And then once we get the power rule, we could probably graph the function and have a pretty good idea of what the zeros of that polynomial are. And from pre-calculus, you know how to take the zeros and use the factor theorem. Using the factor theorem, you can write factors. So when you graph, this is the original function here. When you graph, actually I'd like to see the graph of the derivative. Stick them up. We're looking at symmetry in college algebra today. Ooh, I probably could use one of those. That's okay. We'll graph x. Oh no, this won't feel right. F prime of x equals x to the 4th minus 8x cubed plus 7x squared plus 36x minus 36. Did I do that correctly? Double check me on that. If I look at the picture, x to the 4th minus 8x cubed plus 7x squared plus 36x minus 36. And if I have no idea what the zeros are, I might be kind of out of luck. But if I can graph this, and if the zeros are nice, zoom 6, zip, 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 zip. It looks like intercepts at -2, +1, +3, +6. So judging from that, if even one of those is correct, actually I kind of need 2 of them to be correct to make any progress. But if a couple of these are correct, if the -2 is correct, that means x plus 2 is a factor. If the 1 is correct, that means x minus 1 is a factor. If the 3 is correct, that means x minus 3 is a factor. And if the 6 is correct, then that means x minus 6 is a factor. And we can check to see if any of those are correct just by evaluating it at -2, or 1, or 3, or 6, and they all give us 0. So these are the zeros of this. So the factored form, f prime of x is going to be x plus 2 times x minus 1 times x minus 3 times x minus 6. Now if just 2 of those are actual zeros and the others are close, might have to use synthetic division, depress this polynomial a little bit, and then ultimately the quadratic formula could get it. If only one of them is rational, we are OOL, out of luck, and we're not going to be able to find a way to factor this in a nice way. So it's good that it did factor. So here's the function, but it asks us for maximum and minimum values on specific intervals. So let's look at these specific intervals that it wants. -3 to 0, this closed interval. So if we're trying to find the maximum and minimum values of the function on this interval, we just need the critical numbers that lie within that interval. So critical numbers, or critical points as they are called, are going to be zeros of the first derivative. So if we say x plus 2 times x minus 1 times x minus 3 times x minus 6 equals 0, then x equals -2, or x equals 1, or x equals 3, or x equals 6. So which ones of those are between -3 and 0? -2, the only one, I guess, huh? So just x equals -2. That's the only critical number in that interval. So what we'd want to do is evaluate the function at the endpoints and then evaluate it at the lone critical number in that interval. And that gives us three values. The greatest of those is the maximum value of the function on that interval. The least of those is the minimum value of the function on that interval. And since I have it handy, I'm just going to... no, I don't have it handy. I have the derivative. I do not have the function itself. Bummer that. So I've got to type it in. 1 divided by 5 x to the 5th minus 2 x to the 4th plus 7 divided by 3 x to the 3rd power plus 18x squared minus 36x. Maybe the table feature. So we can evaluate it at -2, at -3, and get -3.6. So f of -3 equals -3.6. We can evaluate it at 0 and get 0. And we can evaluate it at -2 and get 86.933. I wonder if that's a bunch of 3's there. Yeah, 86.9 followed by a bunch of 3's. Approximately. What is the greatest of those three values? So that is the maximum, absolute maximum value of the function on that interval. And the least of those? Minimum. So we just look at that piece of the graph between -3 and 0. So it starts just a little bit below the x-axis, just this piece of the graph right there. The minimum value of the function happens at an endpoint, -3.6. The maximum value of the function on that interval happens at a critical number, happens at -2. So we get the minimum and the maximum on that interval. Yes. Don't have to evaluate it at all infinity. The numbers in the interval, just the endpoints and the critical numbers. Let's see if there's another one of these intervals. I can give four different intervals there. That seems like way too much. Bring that back. -3 to 2. That kind of builds on it. 0 to 4. 0 to 7. How about 0 to 7? Let's do that one. 0 to 7. I feel like I need another copy of that picture. I'm going to put this. Maybe right here. B. D, rather. D. 0 to 7. Which of these critical numbers, which of these zeros of the first derivative are between 0 and 7? One, 3, and 6. So critical numbers 1, 3, and 6. So we want to evaluate it at the endpoints, which we've, I don't know, we've done 0 already, I guess. F of 0 and f of 7. So we evaluate the endpoints, and then we also evaluate it at each of the critical numbers. Here goes. F of 1, f of 3, and f of 6. So 2 endpoints, 3 critical numbers. The absolute maximum and absolute minimum values of the function will occur at one of these 5 points. So f of 0 is 0. F of 7 is what? -10.27 if we round it. F of 1, -17.47. Rounded, of course. F of 3, 3.6. It's curious that f of 3 and f of negative 3 are opposites of each other. F of 6, negative 100.8. If you want another decimal place, negative 100.8. 0. All right. What's the least of these? So minimum. And what's the greatest of these? Maximum. So they both occur at critical numbers. Sometimes that happens. But if we just look at the rest of the graph, let's go light blue here, from 0, I guess it's not all the rest of the graph, just up through 7, which is a little bit less. There we go. There to there. The absolute maximum happens at 3, highest point on the graph in the interval, and the minimum happens there. So both the maximum and the minimum happen at critical numbers for that particular interval. So we specify a function, and there might be several different values where that function could have a derivative that equals 0. But we're only concerned with those that happen in the interval that we're interested in. So it's a function that we're interested in the particular interval of its domain. And the question is specific to the interval. If we just look at the entire function, negative infinity to positive infinity, what's the maximum value of the function on the interval from negative infinity to positive infinity? Well, yeah, I guess you could say it doesn't have one, because it goes up, 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 up. It's unbounded above. It's unbounded below as well. As you look to the left, it has all real numbers in its range. So it has no absolute maximum or absolute minimum value on its entire domain.
Mr. Mazel, the way that you had the factored form was that you graphed the first derivative?
Yes. And I guess bring that back. It looked like this,
yeah.
And I looked at the x-intercepts.
Okay.
So if a polynomial function is equal to 0, then at a particular number, say f of k equals 0, then x minus k is a factor according to the factor theorem. Nice. 4.2. 4.2. Rolle's theorem and the mean value theorem. The mean value theorem will be the one of greater interest to us, but Rolle's theorem kind of leads the way toward the mean value theorem. In certain specific cases, it might be applicable. So I think a picture helps with this. Let's see if I can draw a related picture here. First, Rolle's theorem. Let f be a differentiable function on the open interval AB and a continuous function on the closed interval AB. Now, if it's differentiable on the open interval AB and actually defined on the closed interval AB, it doesn't have to be continuous. And you could have this and then a nice smooth curve, something like that. But this, and having this and this going on, this function is intended to be differentiable on the open interval AB, but it's not continuous on the closed interval AB because it's not continuous from the left at B, it's not continuous from the right at A. It's got to have the right endpoints. Also, if it went off to like negative infinity, something like that, had a vertical asymptote right there, in that case, it would not be continuous on the closed interval, even if it's defined to be something weird at A. So we want to just think what the picture ought to look like if it's nice and smooth in between and continuous there. So we've got this, we've got something like I don't know, maybe something like that. So, if f of a equals f of b. Okay, so I've drawn this deliberately so that whatever f of a is, f of b is the same thing. So the endpoints have to agree. For the mean value theorem, we're going to relax it. And f of a and f of b could be different values. And that's why it's more useful, because it can be applied to a lot more functions. But here we've got an interval, and it's continuous on the closed interval, differentiable on the open interval, and the endpoints agree. F of a is equal to f of b. Then there's at least one point C in the open interval AB where f prime of c equals 0. Maybe a bunch of them, but at least one where f prime of c equals 0. And we're thinking horizontal tangent line here. Visualizing it, there's got to be a point where the tangent line goes horizontal, somewhere between A and B. That can't be avoided. That's what the theorem says. You see kind of where it looks like it ought to happen. It looks like it ought to happen right there. And looks something like that. So that's the C whose existence is guaranteed by Rolle's theorem. F prime of that C equals 0. Okay, so I'm not going to offer a proof of Rolle's theorem, but if we looked at it and try to think, well, could we construct a graph where it would fail, where it would not have, not be a point with a horizontal tangent line? It would force us to draw some sort of point of non-differentiability. It would force us to have maybe an abrupt change in the slope, something like that, where the slope is positive, it's positive, it's positive, it's positive, positive, and suddenly it's negative, it's negative, it's negative, it's negative, it's negative, without ever actually equaling 0. Slope of the tangent line never actually equals 0 on there, but right there at that cusp or corner, whatever you want to call it, the function's not differentiable there. And we're assuming it's differentiable on this entire open interval. So that can't happen and satisfy the hypotheses of Rolle's theorem. It's got to be nice and smooth all the way in between. If it is, and it's continuous, and the endpoints agree, then it will have a horizontal tangent line. F prime will be 0 somewhere in the interval. That's what the theorem says. Let's see if we can apply it to this quadratic function. Find a number C in the open interval from -3 to 5 whose existence is guaranteed by Rolle's theorem. So I just want to make sure that the hypotheses of Rolle's theorem are satisfied on this interval -3 to 5. So there's the open interval from -3 to 5, and then of course it's got to be good. It's differentiable on that open interval, continuous on the closed interval, but it's a polynomial. And polynomials are continuous and differentiable everywhere, so we don't have to stress about that. All we have to stress about as far as Rolle's theorem goes is that the endpoints agree, have the same function value. Well, it says, observe that f of -3 equals -7. Well, from the picture, it kind of looks like, yeah, whoops. Where's -7? -7's right there. So like that. And f of 5 equals -7, so that kind of looks like that too. So it looks like the endpoints agree. We could take -3 substitute for x and 5 substitute for x. Check that out. See if you get -7 in both cases. If not, let me know. But it looks like Rolle's theorem is going to be satisfied here. So find the value of C, whose existence is guaranteed. So f prime of x equals -2x plus 2. We just want to confirm that there's a solution to the equation -2x plus 2 equals 0 between -3 and 5. Does that equation have a solution between -3 and 5? X equals 1. Sure enough. So there is a number in there such that f prime of that number equals 0, and 1 is between -3 and 5. That pretty much does it. C equals 1. And the picture here, that's where the horizontal tangent line happens. So C equals 1. So maybe not that exciting with a polynomial function. With a transcendental function, there's a little bit more going on because we don't have a nice non-graphing calculator way of finding the value of C. We can just be assured, though, that it exists. Use Rolle's theorem to show that the graph of f of x equals x cosine x has a horizontal tangent line in the interval from 0 to pi over 2, and perhaps I should have used the open interval, but unless it happens at 0 and pi over 2 and not in the open interval, then it would happen in the closed interval. So what do we need to check? Well, x is polynomial. It's continuous and differentiable everywhere. Cosine x is, well, it's cosine x. When we looked at the trig functions, basically we said they're continuous and differentiable everywhere that they're defined, and cosine x is defined everywhere. So the product of these continuous functions is continuous, and by the product rule, the product of these differentiable functions is differentiable. So we could do this on the entire real number line. So in particular, if we specify an interval from 0 to pi over 2, let me go open there, to 0 to pi over 2, then it will be continuous and, well, differentiable on the open interval, continuous on the closed interval. So that's satisfied. We just need to check that f of 0 equals f of pi over 2. The endpoints function has to agree. F of 0 is clearly 0. 0 times cosine of 0 is 0 times 1, which is 0. What about f of pi over 2? Well, it's going to be pi over 2 times the cosine of pi over 2. So pi over 2 times 0, and that's 0. So the endpoints agree, and according to Rolle's theorem, we can say, therefore, therefore, Rolle's theorem is an existence theorem. It doesn't tell us how to find the value of C. It just tells us there exists a number C in the interior of that interval, 0 to pi over 2, such that f prime of C equals 0. And at that C, there'll be a horizontal tangent line. So it looks like it happens right there. But I don't know exactly what the value of C is. On your calculator, you can punch this in, do the second calc maximum thing, and it'll give you a nice approximation for it. Mean value theorem has weaker hypotheses than Rolle's theorem, so it applies to far more functions than we could apply Rolle's theorem to. But it's very closely related to this, because what's going on with Rolle's theorem is that we're saying that in between 0 and pi over 2, there is a point on the graph where the tangent line is parallel to the x-axis. Or maybe not the x-axis, but parallel to the straight line connecting these 2 points on the graph. For the previous example, it wasn't the x-axis, it was straight line connecting those 2 points would have looked something like that. But we're saying there's a point in between where the tangent line is parallel to the line between those 2 points. Because it starts out, it's not like that. It starts out, the tangent line is positive slope, positive slope, positive slope, and then it ends up, it's negative slope, negative slope, negative slope, but it's somewhere in between, the slope is equal to 0. Well, the mean value theorem is something like that. See what it says, and draw the picture. whole description here. So similar hypotheses. F needs to be differentiable, nice and smooth on the open interval, and it needs to be continuous on the closed interval, AB. It doesn't have to have the property that f of A equals f of B. F of A could be here, f of B could be way up there. And so we can have a slanted line connecting those 2 points on the graph. That's acceptable, and that's what's going to happen in this picture. So there's A, and there's B, and there's f of A, and there's f of B, and the graph does I don't know what. Needs to pass the vertical line test. Maybe something like that. So let's say that's the graph of the function. If we draw the straight line connecting those 2 points on the graph, like this,
I'm going to check your little plug there. I don't know what the table is.
the power cord.
No, the image was shaking up and down.
Yeah, there it goes.
There it goes again.
Uh-oh. Let's finish
It got worse.
the mean value theorem. What the mean value theorem is saying is that somewhere in between A and B, if all these hypotheses are met, there is a point on the graph where the tangent line is parallel to the straight line connecting these 2 points on the graph. So, not there, not there, not there. Maybe here. Tangent line. Like that.
Even though it crosses the graph again?
Yes. Yes, it's okay. It just needs to have the same steepness as the curve at the point where it intersects the curve. So, the tangent line to the graph is parallel. Let's see what it means here. This is our C. So, f of B minus f of A over B minus A, that's the slope. That's the change in y over the change in x, because this is the point B, f of B. This is the point A, f of A. So the slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, that calculates the slope of the line connecting those 2 points. And then f prime of c is the slope of the tangent line because it's the value of the derivative at c. So the mean value theorem literally says what? The average rate of change of the function on the interval, there's actually a number within the interior of that interval where the function, how to say that? Gosh. The instantaneous rate of change is equal to the average rate of change on the interval. And the situation would be if it were possible to calculate a person's average rate of speed on maybe a toll bridge. Maybe something to check where they checked into the toll bridge and where they checked out. Calculate the average rate of speed. If it could be shown that the average rate of speed was 90, even though the person might have been going 45 at the beginning and 45 at the end, if there's not a
so I guess we're like top 10
right, I guess so. It could be shown using the mean value theorem that there exists at least some point in that interval where the instantaneous rate of speed is equal to 90 miles per hour, and probably greater than that as well. But equal to 90 miles an hour. So that's kind of the idea. The mean value theorem will be used for things other than that when we look at integration. But there's that. Example 3, we can find the value of C, whose existence is guaranteed by the mean value theorem. To see this on here, maybe I can zoom out just a bit. What's that? Yes, I did, and there were several things below that as well. Let me fill this part in. 5 minus negative 1. So on the interval from negative 1, which is right there, to 5, which evidently is right there, find the values of C. There's one is guaranteed, but there are a couple of values in the interval from negative 1 to 5 whose existence is guaranteed by the mean value theorem. Well, find f prime of x. F prime of x is 3x squared minus 12x plus 8. So what the mean value theorem says, there's a number between negative 1 and 5 such that f prime of c equals f of 5 minus f of negative 1 over 5 minus negative 1. So 3c squared minus 12c plus 8 equals, and I wish I had captured it because I don't know what f of 5 is. Let's see what f of 5 is. Let me check and I'll come back. F of 5 evidently is 20, and f of negative 1 looked like it was negative 10. So 20 minus negative 10 over 6. Does it look like f of 5 equals 20? Maybe. That looks like the y coordinate could be 20. And how about f of negative 1? Does it look like that could be negative 10? I think maybe so. So we want to find values of c that are equal to the slope of the line connecting those 2 points right there. The slope of this line is 30 over 6. Or 5. So will there be values of c that satisfy this? Probably. Tell you what, let's take this particular quadratic equation that results is one that's probably best solved by completing the square. You could use the quadratic formula, of course, if you like. But you complete the square, you get c equals 2 plus or minus the square root of 3. This value right here, I believe, is 2. The x-coordinate is 2 plus the square root of 3. I guess it would be about 3.4. It looks on the graph a little bit farther to the right. It's 3.4. Maybe scoot it that way. It's hard to see based on my scale. The other one, 2 minus the square root of 3. No, 3.7. Square root of 3 is 1.7 something, so that's why it looks like it's that close to 4. And this one would be about a little less than 0.3, 2 minus the square root of 3. So you can see these points on the graph are points where the tangent line is actually parallel to that orange secant line, if you want to call it there, the point connecting the line connecting the actual points on the graph. Now, I'm afraid I've got to omit example 4. It's a delightful example where you can actually use the mean value theorem as a significant component of a proof. But it's a lot to think about. I would never ask you something like this on a test, and I'm not going to put it on the homework either. So for your reading pleasure, next lazy Sunday afternoon that you have, you might check this out, and just some leisure reading there as a suggestion. Let's look ahead to 4.3, increasing functions, decreasing functions, and the first derivative test. Now the first derivative test, when we get there, will be one of a couple of tests that we'll use to test whether there's a relative minimum or a relative maximum. But first really modifies derivative. It does not modify test. So it's actually a test involving the first derivative. There'll be another one of these, and that will be a test that we'll use involving the second derivative. And we'll call it the second derivative test. We'll cross that bridge when we get to it. Increasing, decreasing, and constant. We define these in college algebra, what it means for a function to be increasing, what it means for a function to be decreasing. And the definitions don't change all that much. What will change for us as far as our calculus experience is that we'll have a nice theorem for being able to determine where a function is increasing, where it's decreasing, or even constant based on the values of the derivative. So pictures are helpful. They're not everything, but they are helpful. f is increasing on an interval, we like to think of this if the graph is rising as we go from left to right on the interval. So the interval, I'll just say, is the interval I, and if we pick an x sub 1 and an x sub 2 in that interval, and we evaluate the function at x sub 1, and we evaluate the function at x sub 2, and I've chosen this x sub 1 and x sub 2 so that x sub 1 is to the left of x sub 2. So if x sub 1 if whenever x sub 1 is less than x sub 2, it results in a function value for x sub 1 that's less than the corresponding function value for x sub 2, then we say f is increasing on the interval. X values increase, y values also increase. Decreasing, we think of the graph as falling as we go from left to right across the interval. So we pick an x sub 1 and an x sub 2 in the interval such that x sub 1 is less than x sub 2. Evaluate the function at x sub 1. Evaluate the function at x sub 2. Compare them. And if the x's are going from left to right, then the function values are going from high to low. F of the first x sub 1 is greater than f of that second function, f of that second number in the domain. So f of x sub 1 is greater than f of x sub 2 whenever x sub 1 is less than x sub 2, for the function to be decreasing on the interval. And what does it mean for the function to be constant? What does the picture look like? Yep. Got a piece of a horizontal line, just like that. So if we pick, that's the interval I was going for, any two numbers, x sub 1 and x sub 2 in there, evaluate the function at x sub 1, evaluate the function at x sub 2, and compare f of x sub 1 equals f of x sub 2 for any two values in there. So function value never changes. Graph is a piece of a horizontal line. Goes straight across. So that's our definition of increasing, decreasing, and constant. Then we have a theorem. Let f be the function that's continuous on a closed interval, differentiable on the open interval with the same endpoints. Theorem has three parts. If f prime is positive, greater than 0, for every value of x in the open interval where it's differentiable, then f is increasing on that corresponding closed interval where it is continuous. So, picture, let's see. So I'll draw it so it looks like it's increasing. Oops, not quite. Try again. There we go. Maybe it looks like that's increasing on the closed interval. So we kind of needs to be continuous. So we'll include those endpoints right there. There's A and there's B. And what the theorem says, well, what does it say? Be careful. The hypothesis is that f prime of x is greater than 0 for every value of x in the open interval. So it might not be differentiable at the endpoints, but if I'm trying to invoke this right here, then that means that if I pick any number in x in that open interval AB and look at the slope of the tangent line, m sub tan is positive. Is this consistent with what we think of lines with positive slope looking like? We tell the college algebra students if the slope is positive, it goes up to the right. If the slope is negative, it goes down to the right. If the slope is 0, it goes straight across. So visually, it seems to concur with our intuition. And we could turn the picture roughly upside down. Not exactly, but roughly upside down. And we could see if it's going along a function that's decreasing, we would expect the slope of the tangent line to be negative, so that f prime would be negative. Actually need the mean value theorem to prove this theorem. It seems intuitively clear that it ought to be true. But when you think about what does it take to prove that such a thing is true for every value of x in the interval, the mean value theorem comes into play. If I find myself at some point in the near future with extra time on my hands, I'm just kind of looking at the clock thinking, you know, when is it going to get where it needs to go? I'll probably come back and try to prove at least this portion of it using the mean value theorem, because the proof is a little bit interesting, I think. But it's not going to be on the test, so I don't know. I should talk about things that are going to be on the test. Example 1. Find the intervals over which each function is increasing and over which each function is decreasing. Evidently, I'm not expecting the function to be constant on any interval, either one of these. Example 1a. Increasing? Decreasing? Well,
the different areas?
Right, the intervals. On what interval is it increasing? On what interval or intervals is it decreasing? So basically, we just find the derivative and we construct, the first of many sine graphs that we'll do for these functions. We construct a sine graph for the first derivative, and wherever we see pluses on that sine graph, the function itself is increasing. Wherever we see minuses on that sine graph for f prime, the function is going to be decreasing. So, here goes. F prime of x equals 6x squared minus 18x minus 60. Factor a little bit. Factor out 6. X squared minus 3x minus 10. Factor a little bit more. I think that's it. Something interesting happening at 5, something interesting happening at -2. So what we see is a graph of the original function, but I want to construct a sine graph for the first derivative. So here goes. A sine graph for f prime. Now for the sine graph, we talked about critical numbers, also called critical points, in the section before last, section before the Rolle's theorem, mean value theorem section. And we said that on an open interval, if a function has a relative extremum, it must occur at critical number. Critical numbers are also helpful, vital, critical, in the task of determining when the sign of a function can change. So the sign of f prime can only change at a critical number, where f prime is 0 or where f prime is undefined. So we have to consider both of those. Now for this polynomial, f prime is never undefined. It's divided everywhere. So it's only where it's 0. So what are the critical numbers? 5 and -2. So we put those numbers in order from left to right on the number line. -2, 5. This is important. You don't want to put 0 or any other numbers on here because it just causes confusion and clutter. Unless those numbers are critical numbers. Sometimes 0 is a critical number. It's not in this case, but sometimes it is. So just the -2 and the 5. Now, let's evaluate f prime at a number in each of these intervals. So what is f prime of -3? And if we're lazy, sometimes I am, and don't feel like going to the trouble of evaluating it, I can figure out what the sign of it is. That's enough. Just the sign is all I need. So if I can tell if this is positive or it's negative, that's good enough. So if I substitute -3 for x, I'm going to use this expression just because it looks like the easiest expression to use. -3 minus 5 is -8. -3 plus 2 is -1. And -8 times -1 is some positive number. And that positive number times 6 is also a positive number. So that's really all the information we need. Now it's, what, 48? But it's positive 48. That's the important thing. So it's 48 and it's positive. Now here's the thing. The sign of f prime can only change at a critical number. So if it's greater than 0 here, it's greater than 0 throughout this interval. So I'm going to say it's positive there, it's positive there, and there, and there, and there, and there, and there, and there. It's positive for all x's to the left of -2. And so we check f prime of, oh, let's see, so -3 sometimes can be thought of as a test number. Need another test number between -2 and 5. 0 is nice when it works. So test the 0. Honestly, we could use this. It's a little bit easier. 6 times 0 squared minus 18 times 0. 0 kills the first two terms, and we just get -60. So f prime of 0 equals -60. That's negative. So it's negative at 0, and it's negative everywhere else in that interval because it's not allowed to change sign except at a critical number. One more. How about 6? By the symmetry of this thing, I think it's also going to be positive 48. F prime of 6 minus 1, sorry, 6 minus 5 is 1. 6 plus 2 is 8. 1 times 8 is 8. 8 times 6 is 48. So it's 48, and that's positive. So it's positive at 6 and positive everywhere else in that interval. So the function itself is increasing where f prime is positive. It's decreasing where f prime is negative. So I'm going to say increasing, decreasing, increasing, and I guess in front I should say what's increasing, what's decreasing. This is the behavior of the original function f. The derivative is either positive or negative on these intervals. The function is either increasing or decreasing, respectively, on these intervals. So where f prime is positive from negative infinity, basically negative infinity to -2, f is increasing. And where f prime is negative from -2 to 5, f prime is decreasing, and from 5 to positive infinity, f prime is increasing. Look at that. Now, a question that our college algebra book chooses not to address, not to deal with. Basically what it's telling our current college algebra students is we only have to worry about the open intervals when we're talking about increasing and decreasing. And I tell them, I say, life is good now that we're in college algebra, but if you take calculus someday, you might have to consider what's going on at the endpoints. Can we include the endpoints in the intervals where we're saying this function is increasing or decreasing? Now, if it's nice and continuous, yes, we can. And we will. We can include the -2 both in the interval where it's increasing up to the -2 and also include it in the interval where it's decreasing. You have to look carefully at the definition of what it means for a function to be increasing on an interval or decreasing on an interval, but it works in both cases. So I'm going to include it there, or basically I'm going to leave it off there, but I'm going to say f is increasing on negative infinity to -2, including the 2, and 6, is it 6 or 5? 5 to positive infinity, including the 5. F is decreasing on -2 to 5 up. Can include it there as well, like that. But some additional thought has to go into this if we're considering the endpoints. If we're considering the endpoints. So, what about this next example? Can it be done in 4 minutes? Maybe. Maybe if we just kind of visually get this. I think we can differentiate this piece by piece. F prime of x equals 3 if x is less than 2. -1 if x is, notice how I'm leaving off the endpoints, the or equal to bars. 1 if x is greater than 4. Because the derivative fails to exist at 2 and it fails to exist at 4. It causes those values to be critical numbers. Those are critical numbers, not because f prime is 0, but because f prime is undefined. Not only because it's discontinuous there, that would be enough, but it's also there's an abrupt change in the slope. So f prime is never 0, but if we did a sign graph for f prime, we would have the critical numbers. Critical numbers 2 and 4. And I'm just going to look at the picture because I think we can get the picture from, we know what 3x plus 1 looks like, negative x plus 10 and x minus 1. It's easy enough to graph. It's f prime is positive along this interval because it's positive, it's 3. It's negative along this interval because it's -1 along that interval. And it's positive on this interval because it's 1 along that interval. We could pick a test number, but we'd just be evaluating these constants. That's all it would be. So can we say increasing, decreasing, increasing? Well, we can. Let me be as specific as possible. F is increasing on, well, negative infinity to 2. Well, I need dots. There's a dot here, and there's a dot here. There's an open circle there, and an open circle there. Everyone know why? Yeah. Because this is where the or equal to bars are? Yeah. Can I include the 2 in the interval where it's increasing? Well, it's weird. If the dot were here, I would say no. Because it's a jump down from an interval where it's increasing. But it's still going up still, even though there's a clear discontinuity. It's going up. It's a jump up from an interval where it's increasing. And so for that reason, I'm going to say yes. I can include the 2. And can I include the 4 on the interval, this interval right here, where it's increasing? No, because it's a jump down to an interval where it's increasing. If it were down here, I would say yes, because it's going up from wherever that is. But from the whatever f of 4 is, it's jumping down from that. So got to say no. F is decreasing on, can I include the 2?
Yes.
Well, actually, I guess this is an easier question, huh? Because it's solid dots on both sides. This is a lot easier than the others. I shouldn't act like it's a difficult question. I easily get those because it's continuous on that interval. So it's not a difficult question. It's more difficult when there's a discontinuity.